All right, Professor Ronald Mallet, thank you for coming, man.
Thank you.
So it's a pleasure to have you on the show.
Thank you. It's a pleasure to be on the show.
So tell me about your time machine.
Well, I think what we should do is to start back about the real possibility of time travel, because I think it's important for people to realize that it's not something that just I came up with. It's actually something that's based on solid physics. And in fact, time travel to the future is not only solid physics, it's something that we've been able to do. People don't realize that time travel to the future has happened, and we've demonstrated it's time travel to the past that we haven't done experimentally, although theoretically we can talk about it. And all of this notion of the serious possibilities of time travel are based on Einstein's theories of relativity. So I should start off with that and what we know about that, and then go into what my contribution has been. Einstein, back in 2005, came up with a theory about how light behaves with speed. Okay?
What year was it?
2005. Okay. I'm sorry. Back up.
A couple decades earlier, right?
I'm into the 21st century.
Right.
I mean, that back in 1905,
Right.
Einstein came up with the basic theory about how speed is affected.
Right.
How speed affects our behavior with space and time. Okay.
Right.
And that is exactly the root of the possibility of time travel into the future. Now, normally, whenever someone, for instance, throws an object at you, okay, it depends on if you're standing still or if you're running towards them. If I have a baseball, for example, and I'm throwing the ball at you and I'm standing still, it's coming at you at a certain speed. If I'm running towards you and I throw the ball at you, it's going to be coming at you a lot faster.
Right.
In fact, that's what a pitcher does, okay, in order to, on the mound. Now, let's suppose we're looking at light. Let's say a flashlight. Thing is that light, even though it looks like it's continuous, it's made up of little particles of light called photons. These photons are traveling at 186,000 miles per second at you. You can think of them as being like balls of light. Now, suppose that I'm shining the flashlight at you. These balls of light will be coming at you at 186,000 miles per second. But now if I'm running towards you, then just like the baseball, you expect these balls of light to be coming at you faster, okay? Well, when the experiment was done, and it wasn't done with a flashlight, it was an experiment that was done in was 1887 by two physicists, Michelson and Morley. What they found was that if you were shining, and I'm going to be phrasing it in terms of the flashlight, but if you were shining the flashlight at someone and you were standing still, the speed of light was one speed. It would expect it to change if the beam of light was moving towards you. Turns out that the speed was not the light was not affected, okay, at all. It was exactly the same speed. It would be as though I was telling you that baseball was coming at you at exactly the same speed, whether I'm standing still or I'm moving towards you.
Right.
What's going on here, all right? So the experiment, as I said, was done in the 19th century, and it was a puzzle. And it was Einstein who resolved the puzzle. What Einstein said is that the only way that the speed of light should not change, no matter how fast the source of light is moving towards you, is something else has to change. And he said that something is time. Time has to slow down in order to keep the speed of light from changing. So what he said is that, and now think about that again. Once again, what he said is that the only way the speed of light can stay the same is something else does have to change. And that change happens with time. Time has to slow down in order for the speed of light not to change, okay? Now, you might say, well, has that been shown? That's the core of his theory. It has been shown experimentally. In fact, one of the things, and this is, once again, interesting, it's been shown experimentally in many, many things. For example, we have a device that's called a particle accelerator.
Right.
It's at the Switzerland.
Right.
It's the
CERN?
Yeah, CERN, exactly. It's the Large Hadron Collider. And what they do is they take subatomic particles. These subatomic particles can travel at all kinds of speeds, okay? Now, what happens is that some of these particles, they disintegrate after a very, very short period of time. What they do is they find out that if they speed up these particles in these accelerators, they can get these particles to actually live longer than they normally would. What does that mean? That means that their internal clock, think of these particles as having a lifetime.
Right.
And their normal lifetime is, just microseconds, okay?
Right.
All right, fractions of a second. When we speed it up, their internal clock actually slows down so that they actually live longer than they normally would.
So moving through space at any speed automatically slows time down relative to how fast you're going?
That's right.
Or does it? I was under the impression that you had to be going the speed of light.
No.
No.
Any speed. When you're in your car, when you're on a jet plane, the speed. As a matter of fact, this was shown with ordinary passenger jets. Okay, I've used the example of the Large Hadron Collider.
Right, the atomic clock, right?
That's right. But this experiment was done with ordinary passenger jets traveling at the speed of sound. Okay, what they did was they took this at the Naval Observatory, and people aren't aware of this. This was back in the 1970s. What they did was to take atomic clocks, which are the most precise timekeeping mechanism we have. They put one of the atomic clocks on a board an ordinary passenger jet. They put the other atomic clock stationary, okay, at the observatory, Naval Observatory. They flew the passenger jet around the world and brought it back. What they found is that when they brought it back, the passenger jet, the clock on the passenger jet, had slowed down compared to the clock that was at rest at the Naval Observatory. This happened, the passenger jet was only going at the speed of sound, okay? So this shows that at any speed, time will slow down. But the faster we go, the more time will slow down.
Right.
So it has nothing to do with it having to travel at the speed of light. This means that if we have rockets that can go close to the speed of light, then it would be a dramatic effect. For example, let's suppose that an astronaut has a family here on Earth.
Right.
Okay.
Yes.
And suppose that we send them out to on a passenger jet, on a rocket that's going close to the speed of light. When let's suppose that for the astronaut, it only appears that it took them 5 years to go out and coming back from their standpoint. Okay. But their clock has been slowing down.
Right.
Decades could be passing here on the Earth. They could come back and find out that if they had children, their children might have grown up and had children. They could come back and find out that they are younger than their grandchildren.
And that's one of the conundrums to doing this, to sending explorers on a rocket out into deep space, is that, like, if they're traveling close to the speed of light and they're on this rocket for years, time on Earth is going to be moving so much faster. We're going to be developing more technology more rapidly. And, like, just say 20 years or 10 years into their mission, he could have a rocket drive right past him with guys that just left with a belly full of breakfast that morning. And because they advanced in technology so much. So it would be like such a waste of time if technology is just advancing that much faster on Earth to just pass them up.
Yeah, well, Danny, that's a good point. In fact, there's a movie that got it right on that. It was Interstellar.
Right. Yeah.
Okay.
Yeah.
Because that's precisely what can happen, is the fact that the people who left and were traveling at very high rates of speed to get across space, it turns out that for them, even though just a few years are passing on Earth, decades were passing.
Right.
Okay. And that's but the interesting point is that it's real.
That's like, if you think about that, like, what kind of person would it take to go on a mission like that, where you know that everyone you know is going to be, when you can come back, you're not going to know anybody. It's going to be decades have passed, and you're going to, I don't know if you have children. I mean, you're going to have to find people, I guess, that don't have children, that don't have you know, a strong family connection, maybe. I mean, that's a hard thing to do, to be able to disconnect yourself from everything you know in the world and be able to kiss that goodbye going on a mission like that. And you would imagine that it would be far better it would make more sense to figure out backwards time travel before we take missions like that, so we can come back in time, right? And not have to lose all that.
Right. Well, but that's where the problem comes in. As I said, the faster we move, the more time slows down. But no matter how fast you move, you can't make the clock turn back.
Right.
Okay. You can only go into the future. And once again, we've demonstrated that experimentally. That's real. So one of the things that I want people to understand is time travel to the future is not only theoretically possible, it's done.
It's been tested.
It's been tested and it's been done. We just haven't done it on a very rapid scale because we don't have rockets yet that can go close to the speed of light.
So with the plane that was traveling around the Earth close to the speed of sound, what was the time difference between that clock and the clock that was on the base?
Oh, it was only fractions. I mean, was only could be measured by the atomic clocks. Okay, that was part of the problem.
Oh, so it was only fractions of a second.
It was only fractions. That's the reason why it didn't make it into the New York Times. Okay, it was because of that. But that's unfortunately it should have, because it demonstrated what Einstein said, that time slows down for a moving clock, and that it was only a matter of speed, that it doesn't show up dramatically. Okay, but that's why the atomic clocks were used, because it wasn't measurable on a larger scale. But once again, as I said, even when you're on an ordinary passenger jet, time is slowing down for you, but not enough that it's noticeable. But now when they were using astronauts, it becomes even more because they're traveling a larger fraction of the speed of light, okay, than a passenger jet.
Than a plane, right.
Right.
And aren't the satellites that are rotating the Earth traveling?
That's right.
How fast are they going, do you know?
I'm not sure about how fast they could particularly be going, but the thing is that it's happening even for the satellites. But now you might say, well, then can we never go back to the past? Well, we can, but not with that. Now, everything that we've been talking about to this point is called the special theory of relativity.
Right.
So once again, in 1905, the special theory of relativity was developed by Einstein to show, and it showed that time is affected by speed, and it allows for the possibility of the future. Time travel to the past is also possible, but it depends now on a whole different concept. It has to do with gravity.
Let's face it. After a long night out with drinks, the next morning, sometimes you wish backwards time travel was already invented. But I have to tell you about this new genetically engineered prebiotic which makes backward time travel futile.
Sometimes y'all wonder why Danny looks like he belongs to a higher order of human. Not the case. He's just at peace with his body thanks to Z-Biotics.
Now you can enjoy drinks without having to stress about the next day's activities with Z-Biotics pre-alcohol.
It's a vial you drink before your alcohol to avoid rough mornings.
Z-Biotics is the world's first genetically engineered probiotic. It was invented by a PhD scientist to tackle sour mornings after drinking. Here's how it works. When you drink, alcohol gets converted into a toxic byproduct in the gut. It's this byproduct, not dehydration, that's to blame for your rough next day. Pre-alcohol produces an enzyme to break down this byproduct. Just remember to make Z-Biotics your first drink of the night. Drink responsibly, and you'll feel your best tomorrow. I can feel confident socializing late into the night and even record a podcast the next morning. At first, I was on the fence about Z-Biotics. I'm such a lightweight when it comes to alcohol, even a few glasses of wine at dinner will make my next morning a disaster. So I decided to give Z-Biotics a shot. So a couple nights ago, before we went out to dinner, I took a Z-Biotics, had 3 glasses of wine with dinner, and the next day I was on top of my game. Not even I believed how good I felt the next day. Vacations, weddings, birthdays, bar mitzvahs, reunions, get the most out of your summer plans by stocking up on pre-alcohol now. Head to zbiotics.com/Danny and use the code Danny at checkout for 15% off. Pre-alcohol is backed with a 100% money-back guarantee, so if you're unsatisfied for any reason, they'll refund your money, no questions asked. Remember, head to zbiotics.com/Danny and use the code Danny at checkout for 15% off. Thank you to Z-Biotics for sponsoring the show and our party times.
Now, Einstein, reason why did gravity get her into this? Well, it's because of the fact that Einstein felt that everything should be limited by the speed of light. That is to say that light is the ultimate speed limit. All effects shouldn't be able to be going faster than the speed of light. Now, why is this a problem? Well, let's come back to something that goes back to Newton. The Earth going around the sun. What keeps it in orbit is gravity. The gravitational force keeps the Earth in orbit around the sun. Now, let's suppose that there was a cosmic catastrophe that somehow destroyed the sun. Okay. Light takes 8 minutes to get from the sun to the Earth. Okay, that's how long it takes to go that 93 million miles. That means that if the sun was destroyed here on the Earth, we would still see the light coming from the sun for 8 minutes. This is an interesting point. When you look out in the sky and you see the sun, throughout your entire life, you're never seeing the sun the way it is now. You're seeing the sun the way that it was 8 minutes ago. This happens for objects, all stars. The sun is just a star.
Right.
For instance, stars that are 1,000 light years away from us, if that star was destroyed, it would take 1,000 years for us here on the Earth to see it. We would not see the star at the moment it's destroyed.
Wow.
We'd only see
The
it.
light would still be there for 1,000 years?
You got it. All right? So if the sun were destroyed, it would take 8 minutes for us to see that happening.
And that would be us seeing it being destroyed would be 1,000 years in our future.
Well, for a star, for the star.
For a star.
But for the Earth.
For the sun would be
8 minutes.
8 minutes in our future.
Now, but here's where the paradox comes in. According to Newton, gravity travels instantaneously from the sun to the Earth. In other words, the effect of the keeping us in orbit, that's instantaneous. What do I mean by that? That means that if the sun were destroyed, according to Newton, since gravity shuts down immediately, we wouldn't have anything that was holding us in orbit. So we would have the following weird effect. We would see the sun sitting out in the sky, but we would be hurtling off into space because there's no gravity to keep us in orbit. So it would be, what's going on? I mean, if we were thinking about it, because of the fact that we're still seeing the sun, but we're flying off into space. What this implies is that gravity, according to Newton, travels faster than the speed of light.
Oh, wow.
Okay? That's important. And Einstein said nothing, including gravity, can travel faster than the speed of light. That's important. So what he wanted to do was to modify his theory to come up with a more general theory. In fact, that's the name of the general theory of relativity, in which gravity was limited. Okay, so he developed that theory. But when he did that, what he found is that in order to get gravity to do that, in other words, he developed a concept that gravitational force is not really a force at all. It's a property of space. Now, this is a concept that I'm going to have to go back and explain a little bit. There's a simple way of doing it. Imagine that right here we had a rubber sheet, a taut rubber sheet. Okay. And suppose that I had a bowling ball on that rubber sheet. It would be bending the rubber sheet.
Right.
Okay? And suppose that what I did was I had a marble that was on the rubber sheet, and I released the marble. The marble would move down to the bowling ball. Now, suppose that the rubber sheet is there, but it's transparent. Okay? Just say it's a transparent piece of rubber sheet.
Okay.
All you could see is the bowling ball and the marble. So I release the marble. The marble moves down towards the bowling ball. But what you would say, because you can't see the rubber sheet, is you would say, oh, somehow this bowling ball is pulling on the marble. Okay? Because those are the only two things you could see.
Yes.
All right? Einstein said that is exactly what's happening in real space with the sun and the earth. The sun is like the bowling ball, and the earth is like the marble. What's happening is that the sun is bending the empty space around it, but we can't see that bending of space. Oh. All we can see is the earth and the sun. Now, let's go back to the marble again. Suppose I take the marble and I give it a little bit of a sideways motion. And you could do this at home if one wanted to, okay? You
like
could
a funnel, maybe?
Yeah, you could get the marble to sort of move around the bowling ball, okay? If you just gave it, it's like a skater on a roller derby ring, okay? That's what's happening with the Earth and the sun. Fortunately for us, when the solar system was formed, okay, the Earth had a little bit of a sideways motion. So rather than plunging directly into the sun, the Earth goes around and around and around.
Oh wow, that's a cool image.
Okay, that's a beautiful image, as a matter of fact. That's what's happening. The sun is really bending empty space. Now, why is this important? Now, let's go back to the rubber sheet again.
Okay.
Suppose that I take the bowling ball off the rubber sheet for a moment, okay? The rubber sheet's going to vibrate, right? And so that vibration is going to move from the bowling ball up to the marble. If the sun is destroyed, it's going to cause space to vibrate a little bit. But now this vibration, which remember, those vibrations are vibrations of space, but what Einstein said is that this warping of space is what we call gravity. So these are actually gravity waves that are traveling from that vibration, or gravity waves traveling from the sun to the earth. Now, it turns out that if you calculate how fast those vibrations are moving, they're moving at the speed of light. In other words, according to Einstein, gravity can only travel at the speed of light because gravity is the warping of space, okay? And that is, so what that means is that if it's any consolation, according to Einstein's general theory of relativity, if the sun were destroyed, we would see the sun in the sky for 8 minutes, but since gravity only travels at the speed of light, we would still be connected to the sun for 8 minutes.
Oh, wow.
Okay? So we would still see the sun.
Okay.
And we would still be in orbit around the sun for 8 minutes. Now, Einstein had a number of different ways of demonstrating this without having to depend on the sun being destroyed. One of them is a technical thing. It has to do with the orbit of Mercury, but a simpler one has to do with what Einstein found is that because of the fact that you now have limited gravity to traveling at the speed of light, then its effects are like light in motion. That is to say that time is now going to be affected by gravity. Okay? Remember that before we had time being affected by speed.
Yes.
Now, according to Einstein, time is going to be affected by gravity.
Okay.
The stronger gravity is, the more time will slow down. You might say, well, wait a minute, has this been demonstrated in a practical? Not only has it been demonstrated, but it's actually a practical thing that's part of our life. That's
how has it been demonstrated? How is it?
Okay, well, this is this is one of those things that when I'm talking to audiences, they don't realize that it's actually part of their ordinary life, and why it's the GPS. The way the GPS system works is right now, satellites above us are sending a signal down to your unit in your car.
Right.
The signal is happening at a certain time. It's being sent by the satellite. It's being received in your unit at a certain time. The way the system works is there is a basic fundamental relationship that happens it's part of basic physics. There's a relationship between distance, time, and speed. If you know any two of those, you can calculate the other. In other words, if I know speed and I know distance, I can calculate time.
Exactly.
Okay.
Yep.
All right. In this particular case, the way the system works is that I know the time the signal was sent from the satellite. I know the time that it was received in my car. And I also know the speed of the signal, okay, which is the speed of light. So that allows me to calculate distance. That's how your system works. Remember, I said if you know time and you know speed, you can compute distance. All right, so that's what allows you to compute where you are on the Earth.
That makes sense.
All right. Now, here is where the problem came up. When they were setting up the system originally, they were assuming that gravity obeyed the laws of Newton. Why is that important? Because the satellite is orbiting the Earth. That means it's farther away from the Earth than your car. That means that according to Newton, time where gravity is weak is running at the same rate as time in your car because time isn't affected by anything. Okay, including gravity is not affecting time according to Newton. That's important.
Right.
Okay, so when they were setting up the system, they assumed that the time that the satellite, the rate that the satellite clock was moving was exactly the rate at which your unit on the surface of the Earth was running. Okay, the system was giving incorrect GPS locations.
Well, not only is the gravity weaker, but it's moving way faster, right?
Well, there's two effects. That's very good. There's actually two effects that are going on. The satellite is moving rapidly, so time is actually slowing down.
What was it like? You showed it earlier, Steve. It was like 22,000 miles per hour the satellites rotate around the Earth?
I
think that's what it was.
I think it's a mid-orbit.
Yeah, 22,000 miles an hour. That's Oh, yeah, right there.
Right.
Satellites in geo orbit at an altitude of 22,000 miles and travel at speeds around 7,000 miles per hour. These are basic like communication and television satellites.
Some of them travel 30,000.
Oh, wow.
Right.
I think it depends on how high it is.
But once again, though, normally that would affect just the speed. That's the speed of the satellite, but it'd be affecting time. But remember, according to Einstein, gravity is affecting time as well.
Yes.
So that means that since the satellite is further away than the satellite is further away from the center of the Earth than your car is. Okay, your car is closer to the center of Earth. That means that gravity is much stronger where your car is than where the satellite is. That means that the clock in your car unit, because it's close to stronger gravity of the Earth, it's actually running slower.
Right.
Clocks there are running slower than at the satellite. The clocks on the satellite are actually running a little faster than on the Earth, according to Einstein. Okay?
Okay.
All right? Because gravity slows time down. The stronger, once again, according to Einstein.
They would be moving slower, though, right?
The clocks are running slower here on the Earth.
Right.
Than the clocks on board the satellite. It's the opposite. In other words,
okay.
There's two competing effects. That's why I say there's the speed is causing time to slow down. But
low gravity is making it go faster.
Right. It turns out that the low gravity is a greater effect than the speeding of the satellite. So the net effect is that time is actually running a little faster out in space.
Out there. Okay. Wasn't there twin astronauts? One that went into space?
Right. Now that what they were computing in that particular effect was just simply the effect due to speed. They weren't looking at the effect due to gravity. But the thing is that those twins that was done to show that the speed of the satellite was affecting time. They weren't looking at how.
They weren't looking at the gravity.
Exactly.
Okay.
Exactly.
And what was the outcome of that? What they were the same age, right? And then how did they measure like how much he aged?
Well, because of the fact that he was actually traveling a little faster.
Oh, so he's 6 minutes and 5 milliseconds older.
The one on Earth is compared to the guy on board the satellite.
Right.
Okay. Because for him, time is slowing down, so he's not aging as much as his twin brother here on the Earth.
Right.
So the twin brother is a little older. Okay. But if they were looking at the effect of gravity, it would actually reverse.
Right.
But that isn't what they were looking at. Okay. So coming back to the fact that the GPS system, however, was sensitive to the net effect. Okay. That is to say that because of the fact that the gravity is weaker where the satellite is, time is actually going is a little bit faster than your clock in your unit. So your clock in your unit is actually running a little slower because gravity here at the surface of the Earth is stronger than gravity at a high altitude. This happens even at the top of a mountain. In other words, if you use something like atomic clock, and you had it at the top of the mountain, remember, the higher you go, the more gravity becomes weak because you're getting away from the Earth.
Which means the faster time goes.
Right.
Which doesn't make sense. You would think that the more gravity you're in, you would age quicker. Because you think, gravity pulls you down and degrades you.
That's a physiological effect, though.
Right.
See, and in fact,
my brain doesn't work.
No, Danny. What you're bringing up is an important point from the other standpoint, because sometimes people forget that there are two different times that are going on. In fact, we can come back to that because sometimes people will say things like, well, time is just something that we don't even know whether time really exists. It's something that we made up.
Right.
Well, here's what they're correct about.
Guys, being your most comfortable self this fall starts from the waist down. Whether you're gearing up for a weekend on the golf course, sitting on the couch watching football, or spending your time in the gym, MeUndies has got you covered. No matter what your routine, MeUndies comfort is king. That's why this fall I've already got my underwear drawer stocked with MeUndies.
MeUndies has something for every guy this fall. Their micromodal fabric is breathable and comfortable, especially the ball caddy.
Even if you never thought you needed a special pouch for your parts, take the hundreds of 5-star reviews as your sign that this could be your new favorite boxer brief.
So how comfortable are they? Styles for everyone. MeUndies has a cut for every guy's butt. Over 10 different styles ranging from boxer briefs to jock straps to their special pouch underwear called the ball caddy that keeps you from encountering the Batwing ever again. These cuts come in 100 different colors and prints, ranging from black to dinosaurs.
MeUndies isn't just about underwear. Explore the lounge collection featuring joggers, hoodies, onesies, and more.
MeUndies' signature fabric is as soft and warm as a hug from your favorite sweater. It's breathable, stretchy, and oh so comfy, making it ideal for all-day wear.
And it's responsibly sourced. They use sustainably sourced materials and work with partners that care for their workers.
Not happy with your first pair of undies? It's on MeUndies.
Be your most comfortable self this fall with MeUndies. Get 20% off your first order plus free shipping by going to MeUndies.com/Danny Jones. That's MeUndies.com/Danny Jones for 20% off plus free shipping. MeUndies. Comfort from the outside in.
The measurement of time is something we created. But time itself is independent of that.
Right.
Let me give you a simple example because people keep coming back to that. The Big Bang, was the beginning of the universe. In other words, that happened billions of years before we existed here on the Earth. There was no one measuring the beginning of the universe. The Big Bang was the beginning of both space and time. It's hard to get one's head around that.
Right.
But the universe essentially came into existence. Now, you might say, what happened before that? We don't know that. But the thing is that what we do know is that there was a point prior to the existence of time and space where the universe came to existence. And at that instant, the universe, space and time were created at the beginning of the Big Bang. Now, what's important about that is time came into existence, not the measurement of time, but the existence of time. In other words, things exist because it's H.G. Wells had a good way of putting it too. Things endure. In fact, I think of it, of what time is. Time is the persistence of existence. In other words, it's because of the fact that we're talking about. In fact, H.G. Wells had a great example in his book, The Time Machine. You can't have an instantaneous cube existing. It has to endure for a certain period of time.
Stubbornly persistent illusion.
Yes,
that's
right.
What they said in the documentary.
Einstein, yeah, right. The thing is that so it's important to realize that prior to the existence of human beings, there was time. But what we have on a practical level is we measure that existence, how long it takes for something to endure. But that length is independent of any measurement that we make of it. Okay? So that's important to to realize. So when you talk about, for instance, people say, "Gee, well, time seems to be slowing down or speeding up depending on whether I'm giving enough attention to something." If I'm having a good time, time seems to go fast. If I'm bored, time seems to go. Those are physiological effects.
Yes.
Those are things that have to do with, our physiology.
Yeah.
Time itself, though, so there's physical time and there's physiological time. Physical time depends on biology.
Yes.
Okay, physiological time. Physical time is independent of us.
Okay.
Okay, and that's important.
Yeah, and it also seems like time moves a lot faster the older you get.
Once again,
Physiological time.
right, physiological time. But ordinary time, okay, time of physics is independent of that. But now let's come back to why that leads to the possibility of going back to the past, where speed only allows us to go to the future. Okay. Remember what I said about the fact that what gravity is gravity is actually the bending of space. Okay. What we call the gravitational force is just actually the warping of space. The sun warps space. The earth moves along that warp space. Okay, orbits. Time and space are connected to each other, according to Einstein's theories. That is to say, it's called space-time, as a matter of fact. Whatever it is that you do to space also happens to time. Now, if I say that gravity is the warping of space, then that means that time has to also be the warping of space.
Yeah.
Okay? But how does that warping of time show up? The warping of time shows up by the effect that I just mentioned to you, that clocks slow down the more space is warped. Here at the surface of the Earth, space is warped more. Okay? That's what keeps us anchored. In other words, when you jump up and come back down, even though you don't know it, you're actually jumping, you're actually having an effect that it feels to you like you're being pulled down. But what's happening is you're just going along the curved space that the Earth is doing. The Earth itself is curving space around you.
Right.
So when you jump up, in a sense, you might say you're sliding down that curve. Okay. Time, however, when you get down there, time is actually getting, I should say, time is actually slowing down. Okay, so the higher the curve, the more time is less time is slowing down. The stronger as you get closer,
Right.
okay, the more it is.
So how do we go backwards in time? Then?
Okay. Let's suppose that I was looking at a black hole. Let's talk about what a black hole is.
Yes, what is it? Yeah,
Okay.
good.
All right. What a black hole is just simply a star. The way in which stars, our sun is a good example of an ordinary star. What's happening is that right now it's actually what's known as a hydrogen burning engine. What I mean by that is that essentially our sun is a gas ball of hydrogen, and gravity pulls the hydrogen atoms together to form helium.
Okay.
When that happens, if you were to measure a little bit of the difference between the mass of the original hydrogen atoms that collide and the resulting helium, you would find that the mass of the original hydrogen atoms colliding is actually a little greater than the mass of the resulting helium. What happens to that little bit of mass that's difference between that? There's a very famous equation coming back to Einstein again called E = mc squared, which says that mass is equivalent to energy. That little bit of difference of mass is converted into energy. That energy is what we get that gives us life here on Earth. So when the sun, the gravitational forces are pulling the hydrogen atoms together to form helium. The little bit of energy, mass that's different from that is energy that we get here on the Earth, okay? Now, eventually what will happen is that as time goes on, this fuel, you might think, starts getting used up like anything else. There will be a time in which there will be no more burning. When that happens, the star, what kept the sun going, you might say the internal heat pressure, which was pushing the sun out, okay, was being balanced by gravity, which was pulling things in the sun. What will happen is that when that gives out, gravity will overwhelm the star. This happens for our sun, and our sun will start to collapse. Now, if we look at stars that are a little bit more massive than our sun, when they start to collapse, gravity starts getting greater around the star. Now, you don't think about it, but the fact is that light, in a sense, you might say, has some sort of a mass equivalent. It has, weight, essentially. So as gravity gets stronger, light will find it harder to get out of the star. There will come a point when the star starts to collapse to a certain point where the gravity of that star becomes so great that the light that tries to get out of the star gets pulled back to the star.
Okay.
So imagine that you're standing outside and the star is collapsing. And all of a sudden, all of the light that tries to get out of the star gets pulled back to the star. What will you see if you're outside the star? You'll see it like it winks out because you can't see it anymore.
Right.
That's a black hole. A black hole is just simply a star that has collapsed to a point where the gravity is so great around the star that all the light that tries to escape gets pulled back to the star. And so all you would see is a black hole in space because all the light gets pulled back to the star.
So going back to your clear rubber sheet analogy, so it would be the equivalent of like a hole being poked in it?
It's right. That's right.
Okay.
It gets so steep, you might say.
Got it. It breaks through. Okay.
Right. Very good.
How do we actually explore black holes and study them?
Well, the original way that we did it was indirectly because you can't see the black hole. But it was with what were known as binary stars. These are stars that are very common. What they are just simply stars that are orbiting each other. And one of the first of these was a star that was called Cygnus X1 in the constellation Cygnus.
Yes.
What it is that it was a white dwarf star, that was in orbit essentially around a black hole. Now, the gases from the star, I'm sorry, not a white dwarf, it was actually a blue giant. Sorry, it was a blue giant. There are stars, I'm thinking of other systems that have that, but the particular one I'm thinking about, Cygnus X1, what it was a blue giant star.
How big is that compared to the sun?
If you had a blue giant star, it would swallow up all of the inner planets in our system. So the sun's here, the blue giant star would be bigger
than our whole solar system.
Yeah, right. It would.
Wow.
It would be. In other words, a blue giant star would be that big. Okay, so the thing, and it has a blue cast to it. That's why So the thing is that what happened, however, is that we could actually see a wobble of this blue giant star. We couldn't see what was causing it, but the gases of the blue giant star were being funneled into an invisible companion, and it created a halo. You might say the gases heated up.
Oh, wow.
As they orbited the invisible companion. And so even though we couldn't see the inner side of the invisible companion, we could see the halo. That's how we knew that was the first black hole.
So it's like rotating around a black hole?
This blue giant star is, essentially orbiting.
So eventually it's going to go into the black hole.
Eventually all the gases will be pulled in, and the black hole will get bigger, by the way, as the gases are being funneled into the black hole.
Right.
The black hole actually gets bigger the more it takes in.
Wow.
Okay. That was the original one.
Okay.
The more recent
How
one.
far away is that?
Oh, let's see. I'm trying to remember the exact distance, but it's not close.
Not close.
No.
Thank God.
But the one that has been seen originally, that was indirect observation. That is to say, we didn't actually see directly the black hole. What we saw was the gases that were orbiting the black hole. Okay,
right, because they're invisible. You just have to measure the light that's moving around.
Exactly. That's exactly right. The ones that have been more recently, this is about 2017, okay, and the Nobel Prize was won for this, was the fact that they now have direct observation of a black hole. You might say, how was that?
Right.
Well, suppose that you actually have two stars that are orbiting each other, okay, and imagine that as they're orbiting, their orbits become closer and closer and closer, okay? And they smash into each other, okay? When they smash into each other, what they do is they cause these ripples in space that we were talking about, called gravity waves. Remember, gravity waves are actually just ripples of space.
Okay.
So if you have the two stars orbiting and then colliding with each other, they will actually cause a vibration of space. In anticipation of that, here on the Earth, we set up, you might say they were actually gravity wave antennas, so that whenever two stars collided in space, these ripples of space were happening, they were actually being received here on the Earth. And we actually have antennas, you might say, gravity, called LIGO.
Is this what LIGO? Yeah, we had a guy in here named David Chester, who's also a physicist based out in California.
Yeah, LIGO is
he was telling us about this.
Right. LIGO are the gravity detectors. Okay. All right. So they detected, what they actually detect are these ripples of space itself, the gravity waves. And so we're able to actually observe the black hole itself directly. And
now these things, from what I understand, the LIGO technology can create earthquakes or detect earthquakes or something.
In principle, they
something to do
could.
with earthquakes, he was saying.
But their primary purpose was to detect gravity waves from space. That's what they were set up to do. Okay. And the way they actually do it is use laser beams that are at a different angle, sort of 90-degree angle, and then what happens is that as remember when I said a gravity wave is actually a bending of space itself? So imagine that you have a laser beam that's going this way and one that's going, this way, and imagine a gravity wave is coming in. It's going to change the distance because gravity waves are a warping of space itself. It's going to change the distance of the two arms of the antenna.
Right.
And that's what you actually see.
Oh, wow. Okay.
So what you're really measuring is the warping of space itself.
Right.
Due to the collision of these black holes. That was direct observation of it. Okay.
So how do these black holes, I understand what a black hole is.
Okay, so a black hole, but now there are actually two different categories of black holes.
Okay.
There are non-rotating black holes and there are rotating black holes.
Okay.
And a non-rotating black hole just causes a warping of space, that intense warping, okay? But now a rotating black hole will cause it has that same warping, but it causes a twisting effect. One of the things that I like to give people an example of that, in fact, if we had a cup of coffee here, I would be able to show it to you directly, is think of the coffee as being like empty space.
I can get you a cup if you want one.
Well, if you wanted me to show you on that, but
I can imagine it.
Right. So imagine that's empty space. And now,
what the coffee would be.
The coffee would be empty space. Okay.
Got it.
And suppose that and the way I do it in order to do sort of a demonstration, which I've done in some of the documentaries that I've done, is I put a little bit of cream in the coffee so you can actually see a contrast. And I put a little coffee bean in there. So let's suppose that I take a spoon and I start swirling the coffee around. Okay? That's what a rotating black hole is doing to empty space. So not only is the black hole causing a warping of space, but it's causing a twisting of space. And the way in which you can see that in the case of that's the reason why I use a coffee bean. As I say, that's if you want to see the effect, then you can just put a coffee bean in there, and as you're twisting the coffee around, it will cause the coffee bean to be twisted around.
Okay.
All right. That's what rotating black hole does. Now, we actually can see this effect here on the Earth using the Earth. The Earth is rotating. So not only is the Earth warping space, the Earth, as it rotates, is twisting space. Okay. But now with the black hole, this twisting, the rotating black hole is causing an extreme twisting of space. Now, remember what I said, that whatever it is you do to space also happens to time. Think of time, and in fact, this is something that I can do if you have a piece of paper with me.
Oh, can use this one.
Okay.
Here's a pen.
Perfect. Now, what I'm going to do on this strip of paper is draw a timeline.
Okay.
At the bottom of the line, I'm going to put yesterday, the past.
Okay.
At the middle of the line, I'm going to put the present. And at the top of the line, I'm going to put the future. Now, throughout our entire life, this is the way we experience time.
Okay.
Yesterday, here, doing the podcast today, and tomorrow. Okay. Now, this is space, remember. This timeline is in the space of the paper. Okay.
Perfect.
The timeline is in the space of the paper. So you might say this is space and this is time in the space. Okay. But now suppose that I had an object that was rotating space. Now let's see what will be happening to this timeline. This is yesterday. I continue along to today. Okay? I continue along to tomorrow. But look what I've done. I've twisted space so that it has twisted time into a loop. And so what can I do? I can go from the future to where?
To the past.
Right. So by twisting space, I can twist time into a loop. And in fact, if you read scientific papers that talk about that, physicists don't like to openly talk about going back in time. They use the term CTCs, closed time curves.
Closed time curves.
Closed time curves refer to the fact that if I have an object that's rotating space, it can cause closed loops in time. And these closed loops in time can lead to the possibility of time travel to the past. Now, this was done, it was a scientific paper that was written many, many years ago by a man named Carter, who looked mathematically. Everything that we've been talking about as far as this gravity effects, it's a part of what's called Einstein's general theory of relativity. Okay? And so what Carter did was to look at what happened for a rotating black hole. And he was able to show mathematically that it could lead to closed loops in time. And these closed loops in time, theoretically, could allow you to go back into the past. Okay? So Einstein's general theory, so his special theory of relativity allows for the possibility of time travel to the future.
Right.
His general theory of relativity allows for the possibility of time travel to the past. This is real. The difference is that we have been able to experimentally show, not just theoretically, we have been able to experimentally show that speed will allow for the possibility of time travel to the future. We haven't been able to experimentally show yet that the twisting of space will lead to closed loops in time. However, we know that the basis for that is there because we do know that gravity affects time. That's real, the GPS, once again.
Right.
So we do have a real experimental basis. We just haven't created the closed loops in time yet.
Okay.
And that's where part of my work comes in. is there a way that we might be able to experimentally do that? And a number of different ways. As I said already, a rotating black hole could lead to that possibility.
If you had all the money in the world,
Right.
how would you build this time machine?
Okay, well, let me go back and I'll tell you, and you can tell me which you prefer.
Okay.
To talk about my motivation for getting into this, because you might say, why is this theoretical physicist interested in the subject in the first place? And then tell you how my particular contribution, or I could do it in reverse and tell you my contribution and then tell you my motivation.
Let's start right here with how it works, and then let's go into your past and your upbringing and how this all started for you.
Sure. Okay.
I'm sure you've heard me talk about Mando's whole body deodorant at this point. I saw Dr. Shannon Klingman on a video and I couldn't believe it, so I reached out. It's this bar right here, and you can use it on your whole body.
It's dermatologist tested and gentle on your man bits. It controls odor for 72 hours. It's clinically proven. You can choose from 4 cologne quality scents or unscented if you want to go stealthy.
Mando is powered by mandelic acid, and my favorite is their cleansing bar in bourbon leather. And it visibly evens out skin tone and reduces acne scars. Same for their body wash. It's the whole body deodorant that I use, and I cannot recommend it enough.
The starter pack is the best way into Mando, and now new customers get $5 off Mando's best-selling starter pack with code DANNY at shopmando.com. So, what makes Mando so unique?
Mando is seriously safe to use anywhere on your body. Pits, package, grundle and balls, belly button, butt crack, stinky crevices, stomach folds, and feet.
It's created by a doctor who saw firsthand how normal BO was being misdiagnosed and mistreated.
Mando whole body deodorant is powerful enough for the toughest body odor, but gentle enough to use anywhere, allowing you to put Mando on your family jewels without any worry, because Mando is aluminum-free, baking soda-free, cruelty-free, dye-free, and vegan.
Is it clinically proven to control odor better than shower and soap alone?
12 hours after a shower, the average man's grundle odor level was a 5 out of 10. With Mando, the average grundle odor level is 0 out of 10.
That's impressive.
Mando Starter Pack is perfect for new customers. It comes with a solid stick deodorant, cream tube deodorant, and 2 free products of your choice, like mini body wash and deodorant wipes, and free shipping. Luckily, I have a discount code to help you get hooked on my favorite smelling whole body deodorant on the market. New customers get $5 off the starter pack with our exclusive code. That equates to 40% off your starter pack. Use code DANNY at shopmando.com. That's code DANNY at SHOPMANDO for $5 off your starter pack. It's linked below. Now back to the show.
Okay, the thing is that Einstein, let's come back to Newton.
Okay.
According to Newton, the only thing that can create gravity is matter. Okay?
Yes.
In other words, the matter of the Earth creates the gravitational field that keeps us, anchored. Mm-hmm. The gravity of the moon, the gravity of the sun keeps the Earth anchored. Right. Okay, and so on. Einstein's theory says that not only can matter create gravity, but light, pure light itself, can create gravity. That was not something that comes out of Newton's theory at all.
Right.
That's critical. What I realized was the fact that this implies, and this is a simple syllogism, remember that we said that gravity can affect time. Mm-hmm. Okay, if gravity can affect time and light can create gravity, then pure light can affect time. Mm-hmm. Okay? Now, there was a particular device which I learned about because I worked with lasers for a while, or theoretically with lasers. It's a device that's called a ring laser. What is a ring laser? A ring laser is a very simple device. And I'm going to show just one simple representation of it.
So it's like a box with mirrors.
Mirrors are one way of doing it.
Okay.
Okay, I'm going to show one other form. In other words, let's suppose you had 4 lasers.
Up a little bit.
Oh, okay.
Perfect.
Okay, suppose you had 4 lasers.
Okay.
That were shooting beams of light that created this square.
Right. Okay.
Okay. All right. All right. Those light beams will cause a twisting of the empty space in that square. Okay.
How so?
Well, remember that what I said was is that light can create gravity. Mm-hmm. That means this light beam is creating a gravitational field around it. This light beam is creating a gravitational field around it. So there is actually a net gravitational field being created within this region, okay? Mm-hmm. So you might say, and remember that gravity is a twisting of space. So this literally means that these light beams are causing empty space in here to get twisted, okay? Now, you might say, if it's empty space, how will I see it? Remember coming back to that cup of coffee, all right? And I said that if you put cream. If you had cream in there and if you put a coffee bean in there, you could actually see the space to it. Well, the thing that's equivalent here is a particle that's called a neutron.
Yes.
Okay, a neutron actually spins like a little top. Mm-hmm. So if I put a neutron
in between all 4 lasers.
You got it. Yes, exactly. What will happen is that even though I won't be able to see the space being twisted directly, all of a sudden this neutron would start going around.
Right. Okay.
And it would be going around as a result of that.
And you can measure this.
Right. So that's what you would be able to measure. So, and I wrote a real peer-reviewed article about that. That was actually my breakthrough, you might say, and I should mention, I'm a theoretical physicist.
Right.
So when I say that I did this, what I meant was Einstein created a set of gravitational equations they're called Einstein's gravitational field equations. Mm-hmm. And what they do is they tell you for any given type of creation of matter or energy, you can calculate. What I was able to do was to solve Einstein's gravitational field equations for a ring laser, and I was able to show that it will give you this twisting effect. So I did it mathematically. Okay. Everything that I'm telling you is what I've done mathematically by solving Einstein's gravitational field equations. So, but now to do that experimentally that's where funding comes in.
Didn't you already do this?
No, I did it. When I say I did it, that was my contribution with solving Einstein's equations.
No, but in your documentary you showed.
Oh yeah, what you're seeing, but I'm glad you bring that up because that's sometimes people who've seen the documentaries ask about that.
Right.
What that is I had a partner who's a laser experimentalist, and what he did was he said what he was able to do was to show a mock-up, a non-functioning.
Can you find a video of this, Steve? There's a beautiful video of this you might be able to find. It should be on YouTube, right?
Yeah, there is. But this is might say a mock-up. This is actually a model of what it would look like.
Okay. A scaled down version.
Well, it's not only a scaled down version. It is ring lasers, but they're not powerful enough to really create that effect. These lasers have to be much
the problem.
More
we need. That's the biggest problem with building this, right? Is powering
energy.
it.
You got it.
And that's what Jack Sarfati was explaining to me when I was talking to him. He's working on this warp drive, and he was explaining that the biggest problem is the power. Now, are we able to? Now, obviously, you can't detect the electron that's in there,
right? You can't because there's not enough energy, and you actually this is a good representation. This is a toy model of what it would look like. But
yes.
In order to do it, we would have to do the real experiment.
So hypothetically, let's go crazy here.
Okay,
imagine.
Sure. Okay, right.
Professor Mallet, we're going to give you $1 billion to build this time machine in in the basement at DARPA or whatever.
Right.
And we want to figure out how to do this. Where would you start? What would you do?
Okay. The first thing I would have to do is a two-step process. One is I have to show that the circulating beam of light actually causes a twisting of space. I've been able to do that mathematically.
Okay.
But first, that's the first step. The energy that's necessary to do that, while it's great, is within our technological capabilities, okay, to just twist space. The twisting of time, however, is the next step. The twisting of space happens at lower energies. In other words, for instance, the Earth, the Earth is, because it's rotating, is causing that twisting of space. But you might say, isn't it doing the twisting of time? No, because the rotation of the Earth isn't great enough. You have to have a rotating black hole in order to do that. So, but there have been experiments that have shown the twisting of space, okay? So we do know that a rotating object will cause a twisting of space with matter. We haven't been able to show it. My prediction is it's not just with matter, but with light. That's the difference. That experiment hasn't been done. It's been done mathematically, but it hasn't been done experimentally. But now, even though once we do that, then the next step is to say, okay, I have now the necessary, but is it sufficient condition? That's the next step. And it turns out that in order to have the circulating light beams cause the twisting of time, in addition, has energy. We're talking about galactic scales of energy.
Really?
For that. Oh, yeah. That is a whole different level of energy. And you might say, well, then is that going to be forever out of our reach? No, two things. One, what we have to do is become creative. In other words, we have to figure out ways that we can bridge that energy gap. What might be ways that we might reduce that? One of the things that I haven't talked about at all here, and this is a whole different level of argument and discussion, is quantum theory. The foundation of modern physics is based on two pillars. One is relativity, the other is quantum theory. Both of these are part of modern physics. You might say matter and energy have been, the notion about space and time, that has become relativity. Matter and energy has been quantum theory. In other words, our understanding of matter, of atoms, of the nucleus, of atomic energy, all of these things are part of quantum mechanics.
Right.
All right. I haven't done that part of it yet. I haven't put in quantum mechanics into this yet. What I need to do first is to show the twisting of space, and then I need to analyze that and look at what might be able to overcome that barrier. Has this happened before? Yes. When we were talking about Einstein's famous equation equals mc squared. When this equation originally came out, it was clear that you could use, if you could convert matter into pure energy, you could have an enormous amount of energy from a small amount of matter. Okay. The question was that practical? Einstein originally wasn't even sure that would be practical. It wasn't until the 30s when quantum theory was developed later. Okay, the original quantum theory was developed at the beginning of the 20th century, but quantum mechanics came out later. And it wasn't until the 30s with the understanding of chain reactions that we knew a practical way of converting matter into energy. So what I'm saying is that even though we had the theoretical possibility of converting matter into energy, it wasn't until we had quantum mechanics that we saw the practical way. So what I've done is I've used relativity to show this. But as far as practically overcoming the energy barrier, that's going to have to take other technological breakthroughs, which haven't happened yet.
And then once we were able to do it, how would we figure out, how would we find a place to aim at? How would you know how far back you're going to go? Or
two things, right. One of the things is what would be a practical way to know that we even have been able to do it.
Yes.
Okay. And this is, once again, part of what I've looked at, and that is how would you practically know it? Remember we talked about the fact that the faster an object moves, the more time slows down, okay? And we can actually see that effect. There's another aspect of particles. Remember I said that they normally take they decay after a certain time, some particles. They in the Large Hadron Collider, there are subatomic particles that only can live for a very short period of time. And when we speed them up, we can get them to live longer, okay? Now, imagine that I was sending something back to the past. When I send something back to the past, and actually one of the science fiction movies played on this idea, what would happen if you went back to the past and lived to the present time? Okay, so let's suppose that Danny, today, you went back to the past, okay, and then lived in the past to the present and met yourself here. What would you see? You would actually be seeing an older version of yourself now because you have lived from the past to the present.
Right.
Okay? That's what would happen with subatomic particles. So what would happen is that it would be the reverse of what happens normally with speed. In other words, if I send something back to the past, it would live a shorter period of time than it normally would have because it would be older.
Okay.
Okay?
I'm trying to grasp this.
In fact, as I said, one of the science fiction movies was one of the Marvel movies where I think it was Captain America decided to live in the past with a young woman that he had met. And then he meets his friends again in the present. But now he has lived from the past up to their present, which means now he's an older version of himself when he meets them again.
Right. Okay, I understand. That makes sense.
You see what I'm saying?
Right.
So that's weird, but that would be the way you would do it. In other words, what you would say is that, oh, good heavens, I've changed the lifetime of this particle, but rather than making it live longer, I would find that I would be making it live shorter.
Yes. Yeah, that makes sense. Have you heard of there's I think it's a Harvard physicist by the name of Len Howe. My friend Jeremy was explaining to me there was somebody named Len Howe who was at Harvard and figured out a way how to stop and reverse light and was doing some experiments similar to what you've been doing.
Oh, well, there's actually experiments.
Can you find that, Steve?
There's actually experiments to slow light down, to actually cause light to stop. Those are different type of experiment from when, because it's not that I'm actually trying to affect light itself. I'm using the fact that I'm using gravity of light. This is a whole different, thing. In other words, what I want to do is to use light to control time rather than controlling light itself.
Yes. Okay. Yeah.
Okay.
Oh, is this Harvard Gazette? Oh, okay. Is this Len Howe?
Yeah. Oh, in fact, that's
2 years ago, we
slowed
it down to 38 miles an hour, and now we've been able to park it, then bring it back to full speed. Len Howe isn't talking about a used motorbike, but about light, the ethereal, life-sustaining stuff that normally travels 93 million miles per hour from the sun in about 8 minutes.
Right. This is extremely important fundamental experiments, but they're controlling light itself, whereas I'm using light to control gravity.
Right.
And to control time and space.
That's why the atom cloud was suspended magnetically in a chamber pumped down to a vacuum 100 trillion times lower than the pressures of the air in the room where you are reading this. Wow.
These experiments that are used to control light, they might have an implication for what I'm doing. Insofar as the fact that if you control light, then, and since if you control light and light controls gravity, then you could perhaps use some of these experiments to indirectly control gravity as well.
Yes.
But what I've been focusing on directly is using light in different configurations to try to control time, space and time. And once again, it's important to realize that I'm talking about two interrelated effects. First, I have to show that using circulating light will cause this twisting of space. And then once I've shown that, then I can move on to show that the twisting of space, if it's strong enough, will cause a twisting of time.
So can you explain how it works? Like, if we were to create a time machine, figure out how to turn on a time machine today, we would not be able to travel back in the future before we were able to turn that machine on.
That's right.
Why is that?
Well, because of the fact that it's cause and effect. Remember that the thing that's causing the twisting of space, let's go back to the ring laser. When I turn on the ring laser, the circulating beam of light will cause this twisting of space. But now, before I turn the machine on, is there any twisting of space?
No.
Right. But it's after I turn the machine on. So suppose that I turn on the machine and I start twisting time. Okay, time will start getting twisted into a loop at the moment I turn the machine on. And so if I leave the machine on, let's suppose I leave the machine on for 10 years, then someone 10 years from now potentially could send back information 7 years, 5 years, all the way up to the time I turn the machine on. But they can't send it earlier than that because there's no loops in time prior to my turning the machine on.
Right. So, okay.
Okay? So, but one of the things I mentioned in a History Channel documentary is the fact that we're talking about terrestrial time machines. Suppose that, that we know now, and this is no longer science fiction. We know there are what are known as extrasolar planets. These are planets that are revolving around other stars. In other words, we know that there are other solar systems out there, and that these other solar systems have planets revolve around. That was discovered scientifically back in the 90s. Okay. All right. And we know now that the universe is teeming with these extrasolar planets. Okay. What physicists now, and they like to use clever names, is that some of these planets are too close to their stars to support life. Some of them are too far away.
Yeah.
But there's actually a zone.
Goldilocks zone.
You got it. The Goldilocks zone. And so it's highly possible, even though we haven't discovered yet, that there are planets that probably are teeming with life out there. Now, suppose that these civilizations, some of them were created many, many, many eons before us and have become advanced enough to turn their device on. Suppose they, relative to us, if we found them, let's suppose they turned on, that's their 10,000 years, ago. When we go to their, planet, we could use their device to go to our past, but it would still have the same limitation. And this is so even for a rotating black hole. Rotating black hole, before the rotating black hole was created, there was no twisting of space and time.
Right.
After it was created, so if we could find a rotating black hole that had existed long enough ago, once again, this is interstellar, we could go back to our distant past. Okay, the question is that, and in fact, this is something that was mentioned, or we should talk about, is people have talked about UFOs.
Yes.
One of the speculations has been that sometime in the distant future, we may have been able to find other civilizations, extraterrestrial civilizations, that had time machines turned on earlier than ours. Once we do that, it could be that we could visit ourselves in the present or any other time in the past by having contacted that civilization.
Wow.
So
okay. Wow.
So what we call UFOs
could just be time machines.
Could be time travelers from our own future who have come to who have made contact.
I was explaining to you before we started, I had a guy on here recently by the name of Michael Masters, who's an anthropologist. And he got into the field of anthropology because he was always fascinated with UFOs and all these documented accounts, numerous, hundreds and hundreds and hundreds, thousands of documented accounts of these abduction encounters. There's a famous Harvard psychologist, John Mack, who studied this for his whole life. And he interviewed all these people who had these crazy abduction experiences, and he cataloged all of them. And I think it was a 70-30 split. 30% of these abduction experiences, they explain these beings saying that they were from different star systems. 70% of them, you might want to correct me on that, it's close to 70. 70% of the people said that these beings said that they were from the future. And almost all of them, all of these abduction experiencers explain human beings being in these crafts and doing these experiments. A lot of them are like reproductive experiments, like extracting. I don't know if you're familiar with Betty and Barney Hill.
I've heard of
that's
them.
a famous one where he explains they
yeah.
extracted semen from him and like eggs from his wife. And they seem to be some sort of reproductive experiment that was going on in like over 90% of these cases.
Right.
So what Michael Masters, the the idea he lays out is that from an anthropological point of view, if you look at Earth, there's over 2 million cataloged species of animals on Earth. Right. 20 of the 2 million are hominids, which is like 0.001% of the species on Earth are hominids. Now, out of the 20, one of them, us,
right,
has figured out how to develop technology to leave the Earth. Now, think how rare that is just on Earth,
right,
for people to develop, for a creature or an organism to develop this kind of technology. Now, extrapolate that out into the universe and all of the habitable planets out there that are habitable for life. Most of them, which I believe are water worlds, from what astronomers have told me. What is the likelihood that they're going to look just like human beings?
Yeah.
It's got to be so small. So that's one of the arguments he lays out to why these could be future humans. Another one is that most of these experiences where people had contact or were abducted,
right,
these beings seem to be very, very invested in the future of planet Earth. Like, you have documented of UFOs hovering around, shutting down nuclear bases, telepathically communicating to children how they need to preserve the Earth and be careful with technology. Most of these things came around when nukes started being tested. There was the most UFO sightings ever. If you look at, there's a great animation that was done where it basically showed all the testing of nuclear weapons throughout history. And the most UFO sightings happened when we started testing nukes. So if these things started showing up and communicating to people just to respect and try to preserve the planet, they obviously have a vested interest in the planet.
Right. So
who would have more of an interest in preserving this planet? Would it be future us, or would it be some civilization from light years away? So that's really interesting. And he also has another thing that he lays out, the schematics. He lays out how, and this might be something you can find, Steve, on how the actual layout of the flying saucer UFO that we're all aware of, it could be a time machine. The way it works, it could just be that thing is built to travel through time. Mm-hmm. So yeah, it's really interesting. But if they're coming back to, I mean, most of these abduction experiences happened during the 80s and 90s, mostly in the 90s. Right. If we hadn't figured out a time machine then, how did we originally get it? And that kind of goes back to some of the recent things that have been coming out with like David Grush and Diana Pasulka. They explain these things as like gifted to us, these crash retrieval sites like Roswell and others. They explain them as, you know, they were gifts to us. So like maybe somewhere on Earth, some deep government program or some aerospace company has these things, and it's sort of like black project technology that nobody is aware of. Congress has been restricted from having any kind of information on this that we figured out a long time ago, that the public just doesn't know about.
That's a possibility. However, the thing is that I think we have to give ourselves more credit than being gifted. The reason why I'm saying two different points. Number one is we as people are terribly have a problem with keeping secrets.
Yeah, we do.
Okay, and the thing is that all we have to do is go back to the Manhattan Project.
Yes.
To know, you know, they had as tight a security as we've ever been able, and then someone just essentially walked out with the. You know, in fact, they were looking at the scientists who were close to the program, very close to the program, and there was this one outlier scientist who wasn't anyone's, and he just walked out with his. I think his name was Klaus Fuchs, with the information that was able to share it with the Russians. I mean, so everyday people would have a hard time getting these secrets, but if the government was doing it, it would have leaked.
Well, there's lots of leaks, though. There's so many stories.
Exactly.
There's Bob Lazar's story. The problem is there's there's so much disinformation and misinformation, and we don't know what's real and what's not. Like, I was talking to my buddy this morning about this. I'm like, the world that we know it right now, information is everywhere. Right. And there's so many crazy stories. It's like, how do you pick what's real and what's fabricated or what's strategic? I mean, we know strategic deception is a technique that's been used by the military and intelligence for forever. So, like, just looking at humanity and how we look at reality right now. If the government came out tomorrow, look at how many people trust the government right now, right?
Right.
If the government came out tomorrow and said, "Hey, aliens are here," how many people do you think would believe it? Or how many people would think that, oh, the government's just trying to play some game with us?
Well, but once again, as a scientist, I have to see proof, and that proof has to be independently looked at. But coming back to you actually mentioned part of it. Who would it be more likely to want to come back to warn ourselves about what's happening to our planet? Would it be some other future civilization or us? Suppose that we were able to, in fact, find extraterrestrial civilization that had time travel much earlier than we did, and we were able to convince them to allow us to use their time travel technology to come back to our past.
Yeah.
Okay. To me, that's really much more likely, scenario. Of course, that means that we would have had to learn to develop space travel to the point that we could actually find these civilizations. But all of these things are just, pure speculation. The main point is that time travel to the past is possible, and there are ways in which we could travel back to our earlier time. Okay.
So hypothetically, if a time machine was turned on in another galaxy far, far away, and we somehow got it here,
right,
we would be able to travel back into our ancient past.
That's right.
Okay.
That's right. That's the upshot of that. And that to me is the important thing, is the fact that we do know that there are ways of manipulating space and time. And we know it's based on real solid science that's independent of a political beliefs or anything. It's just solid physics. Okay, based on the person who was named the person of the century last century. Okay, Einstein. That's the reason why I believe in the work, is the fact that it's based on real solid science. Okay, and the other thing that's beautiful about science is that it's been developed by all different countries and all different civilizations, and it's independent of that our particular, political or beliefs. But for me personally, the reason why I got interested in the subject in the first place had to do with a very, very personal story, and it's still playing out for me, by the way. And I'll tell you why. When I was 10 years old, I was brought up in the Bronx, New York. And my father was a television repairman. He served in the Army, and he used the GI Bill when he came out in the Second World War to become a electronic technician. And he was very good at his job. For me, his sun rose and set on him. Okay, he was a very, very dynamic, fun person. Okay, and he didn't look like he was sick. He looked like he was extremely healthy. Mm-hmm. What he did was he died of a massive heart attack when he was only 33 years old. As I said, I was 10 years old. And to say I was completely devastated is actually an understatement. I can't find a word for it, but I didn't really care whether I lived or died after he passed away. One of the gifts he left me, though, during his life was a love of reading. And I read science fiction. And after he died, I came across the book that changed my life. It was H.G. Wells' The Time Machine. It was a Classics Illustrated edition of it. And what it said at the very beginning of it, it said, scientific people know very well that time is just a kind of space, and we can move forward and backward in time just as we can in space. Now, to my 11-year-old mind, I thought, wow, if this is saying that we could move back in time, then maybe if I had a time machine, I could go back into the past and see him again and tell him what was going to happen. So that became an obsession for me to do it. In fact, I even tried, he had left, after he died, my mother kept his television and radio parts. I even tried to put something together that was illustrated on the Classics Illustrated book. Of course, nothing happened, but I remembered that it said scientific people know very well. So I knew that science was going to have to play a role in it. It's interesting. I written a book, by the way, that talks about this, right?
Time Traveler.
Yeah.
A scientist's personal mission to make time travel a reality. By Dr. Ronald Mallet.
Yeah, and
When did you publish this?
that was published in 2006. That's when it
okay.
came out, and it's been republished. Now. The thing is that, and it's been translated into a number of different languages, by the way.
Oh, wow.
And a number of documentaries have been made about it. There's even some speculation that perhaps it might be made into a Hollywood movie eventually. Mm-hmm. But the thing is that when I learned a little bit later that there was this great genius named Einstein who said that time, in fact, can be affected by some way. And I knew that if I could understand Einstein, I might be able to understand how a time machine might be built. And so I dedicated my life to that, to that end. I should mention that when I was growing up, this was in the 50s, this was around the time of Sputnik, people didn't even know whether we could go to space, let alone time travel. So I kept this a secret during my life. Now I can talk about it openly. Here I am on your podcast talking about it. But when I grew up, I had to keep it secret. I kept it secret all during my life. Even in my career, I tried to study something that was close enough to it, which were black holes. That's what my career was based on. So that I could keep it. I wouldn't have become a professor at UConn. Imagine if I had, during the interview, they'd say, well, what is it you're interested in time travel? I wouldn't be here. The thing is that, but I made my breakthrough literally at the beginning of this century, the 20th century, is when I realized that, according to Einstein, there was possibilities of affecting time using light. And that's when I had my particular breakthrough with showing that a circulating beam of laser light can cause, mathematically, cause a twisting of space and time, as I said, by solving Einstein's gravitational field equations. For me, though, it goes now beyond just looking at what I might have been able to do with my father's life. It's just imagine for future generations if we were able to travel back in time. For example, just the simplest example, imagine if we had been able to send information back to ourselves about COVID prior to all of this, the millions of lives we could have saved, or the catastrophes that happened with hurricanes and tsunamis and everything, by being able to send information back to ourselves. Of course, it's romantically great to be able to say, we'll go back in time, but just sending information back to us, what we could do. So that's become important to me too, is what could we do as human beings to improve our lives by being able to have change our destiny. So that's why I still think it's extremely important to have this possibility of time travel, even for future generations.
That's fascinating. So that's what basically sparked your whole interest in this. And have you you've thought about the documentary, by the way, How to Build a Time Machine is a fantastic documentary. But towards the end of that, you kind of elucidate the paradox of if you were to go back and meet your father. You've thought about this quite a bit.
Oh, yeah. Yeah. Well, the thing is that there's two things. One is that what would that mean as far as the reality of it? Because, for example, there's two things that my father could ignore my advice, and that would just simply lead to the past and the present that I'm living in. Or what happens if he takes my advice and changes his life? What happens to the future that I live in, this part of the future? That is another reason why both philosophers as well as the general public have said it's time travel to the past, possible, because there's no paradox when you go to the future.
Right.
When you go to the future, you leave everyone else and you just come back to the future. If you go back to the past, you change things that can affect the entire, universe, okay? Quantum mechanics plays a role in this. That's where quantum mechanics is. As I said, all of our discussion, we haven't talked about that role. Quantum mechanics is a whole different beast.
Now, does quantum mechanics work in the block universe idea?
Block universe is a possibility. I mean, quantum mechanics is sort of independent of these different versions of, the block universe. Okay. It's you might say it's the quantum mechanics is about the foundation blocks that build up our forces of nature. Okay. And these things happen within that quantum universe. Okay. So Quantum mechanics, however, does allow a resolution of the paradox in the following way. What quantum mechanics is based on is the notion of probability. To give you a specific example of what I'm talking about, whenever we talk about making a prediction, for example, if you say this evening you're going to the restaurant and say that you're looking at a menu and you see item A and item B on that menu, you make a choice of that, and then you live with that choice. Let's say you make a choice of item B. Okay, that's it.
Mm-hmm.
Quantum mechanics says is that, well, there is a probability that you could have chosen A.
Mm-hmm.
Okay, now there is a theory. It's called the many worlds interpretation of quantum mechanics. What this interpretation says is that at the instant that you chose item B, there is actually a split of the universe. There's a universe in which Danny Jones has chosen A. So when you go into that restaurant and chose B, there's a split. There's a real you in another universe that's chosen item A on the menu. They do not know about each other at all. They become separate parallel universes. And in fact, the original notion of this was based on a physicist back in the 1950s named Hugh Everett III. And his research led to this possibility of parallel universes. Okay, this means that this is how it would resolve the time travel, portion. Suppose you travel back into the past. As soon as you arrive in the past, there would be a split of the universe.
Right.
There would be a universe in which you arrive in the past, okay, and in that past, you do create something. Like, for instance, in my case, I do affect my father, okay, and I do change that past. I find myself in a weird universe that I wasn't born in, okay, because the universe I was born in, he died, okay, but I've changed that universe. So there's now a parallel universe with the me as an adult me, and there's a young boy me. And even though we look exactly the same, I'm an older version, me.
You're both existing in the same time and place.
Right. But remember, I said that there's a split.
Yeah.
The other universe I don't arrive in at all.
Right. The one that you were originally in.
Right. And so that parallel universe plays out. So in other words, even though I would be able to save my father's life in universe B, I didn't save his life in universe A.
Right.
Okay. And there's no paradox with me having saved his life in universe B because I never came from universe B. So according to this notion of parallel universes,
Right.
okay, and you might say, well, couldn't I go back into the past? Well, it turns out that you would just be universe hopping because every time you try to go back, you would just come back to another parallel universe. So you would never be able to go back to the universe that you originally came from. So that is the way in which quantum mechanics potentially can resolve this paradox, okay? But now you might say, is it possible that you really do change the universe and everything? Well, we don't know until we do the experiment. That's the whole point.
Right.
But there is a possibility that it plays out as, just parallel universe.
Wow. Now, so from my understanding of like the block universe is that it's like you imagine slivers like a block, like a million sheets of paper stacked up on top of each other, and we're living on one sheet of paper right now, and all the other sheets of paper are already created, right? Like some cosmic toddlers drawing pictures and stacking them on top of each other, and everything is already laid out. So that would mean that our future is already predetermined, right? And that would basically mean that free will isn't real.
You're right. That is not consistent with quantum theory.
Right. Oh, it's not completely inconsistent with it. Okay.
Yeah. I mean, that's why I'm saying that anything that says that everything is already predetermined, once again, quantum mechanics says that we're talking about probability. I can say this is quantum mechanics sounds a lot weirder, but if you go back to basically what it said, it's based on something that was called Heisenberg's uncertainty principle. It's a lot simpler which says that I can know the position of an object precisely, or I can know the motion of that object precisely, but I can't know both of those two things at the same time precisely. Okay? That's essentially Heisenberg's uncertainty principle. Okay? Which doesn't sound quite as exotic.
Right.
But if you look at what that means as far as information is concerned, in ordinary classical physics, you can make precise predictions about what's going to happen next if you know exactly the position and motion of an object at a particular time. And what quantum mechanics says is I can't know that. If you build into that now, and this is going a lot deeper into it, what it tells you is that I can make a probability prediction about what may happen, but I can't make an exact prediction about what's going to happen. So that means that the future isn't exactly determined. I can only talk about the probability of the future. So I could actually have this stacking that you're talking about, but it would be sort of a probability built into that stacking as well. So it's not that the future will play out, okay, but we can't determine exactly how it will play out. We can only talk about the probability of how it plays. And we know that that's the way in which the universe works. Why? Because we have cell phones. We have, computer. All of our modern technology is based on quantum physics. So this exotic sounding theory has led to our ordinary technology, which wouldn't work, by the way, if it weren't for quantum theory.
Right. Yeah. Now, and another thing that you talked about briefly in that documentary is sort of like the way the funding for research for some of this stuff goes is that it's only funded when there's some sort of a necessity. Like if we found out that North Korea was trying to build a time machine, then we would all of a sudden have all the incentive in the world and all the money in the world to build a time machine.
Exactly.
And that's how it's worked throughout the history of the world.
Exactly.
Like if we find out somebody else is doing it, we want to jump on it.
Yeah. And unfortunately, that's the case. I mean, even when it came to our being in space. Why? It was Sputnik.
Right.
Sputnik is the reason why we landed on the moon.
Mm-hmm. Yeah, and isn't it crazy that we haven't been back since in how many years? Like 50, 60 years we haven't been back to the moon.
We don't have a real incentive to it. It's just not something that and once again, it's unfortunate that it has to be this catch-up game. To me, going to Mars is just exciting in and of itself, but it doesn't have a real practical application. However, the space program did. Personal computer, all of these technologies that were developed are developed as a result of that. Even when it comes to what I was talking about as far as twisting space, using the ring laser. Someone had asked me, well, is there a practical spin-off that would come from that? As a matter of fact, there would be. Why is that? Information transfer, okay? How do we transfer information? We transfer information by sending things through space. Wires. I send electrons through wires, okay?
Right.
I send information through space. But what would happen if not only did I send information through space, but I sent information with space? Let me give you a simple example. You're sitting in a bathtub. Mm-hmm. Think of the water as being like space in the tub. Now, what can I do? I want to get to the bar to the other side of that tub. I push it along the water. It moves to the other side. But what would happen if, in addition to my pushing it through the water, I hit the water itself? Not only now am I transferring the soap through the water, I'm traveling the soap with the water. So I can actually make it go faster than it would if I was just manipulating the information through space. So by manipulating space itself, I could actually cause transfers of information to happen at speeds that we're not even, we don't even think about now.
Yes.
That's a spin-off.
Yeah. And again, going back to what we were talking about at the beginning of the conversation with travel out into, deeper parts of the galaxy, is that backwards time travel is a practical thing that we would need to figure out if we want to send human beings, because they're gonna be going on that rocket ship on rocket time while we're on Earth time going, 100 times faster than they are. So we would want to figure out backwards time travel before we started doing that. It would make more sense to have.
If we could send ourselves information, but then there's a paradox to that, okay? If we're sending information back to ourselves, okay, then we have to have been able to figure it out, how to do it.
Yes.
Unless, once again, we have some sort of other means of having access to another device that would allow us to send that information back. Then you would be changing your timeline. You know, there's all of these other aspects of this that have to be thought about. Basically, however, physics is an experimental subject. And so all the things that, once again, we're talking about is speculation, but it's anchored in the possibility, real possibility, that we can manipulate space and time.
Do you think it's possible that there is somewhere in some program that they have figured this out and they're just keeping it a secret from us with some sort of Manhattan Project layer of security and secrecy wrapped around it?
I don't know. I mean, I really don't know. The thing is that I can believe, once again, I can believe it. I would like to say that I would actually hope that that's happening. I would like it to be based on my work. But once again, it costs money to do these things. And we have a tendency to say, well, is this really going to be that important? I mean, is this going to be something that we really want to invest in? And I don't know. I mean, I really don't know. I mean,
well, that's like some of the stuff that like David Grush was talking about, right? All of the money all the black money that's been going into these programs that has been completely, Congress has been completely oblivious to. He's basically pointing out that there's like huge swaths of money that are going to these companies, these aerospace contractors, and and it's not passing Congress, but they're just somehow like siphoning them billions of dollars to work on some stuff that we don't know what the hell it is.
Yeah. That's, I mean, as I
like
said,
blue sky research, right?
Yeah.
Like that's some of this, like one of the things that doesn't happen as much, at least the public's not aware of, is this idea of blue sky research, right? Like throwing money towards some sort of project that we don't know how it's going to benefit us monetarily or militarily, right? In the future.
Right.
Like, let's just throw money at something and try to learn something new. Well, no, it doesn't make sense. Like, we got to make sure that we can cement ourselves as a superpower or make a lot of money or increase our GDP, whatever it might be.
Yeah. I'd like to have some of this blue sky money.
Yeah, right?
Really, that's what I think. And to me, it's important to have that, you know, because of the fact that we don't know what the possibilities are, but the possibilities are based in real science.
What do you think would be some of the things that would be necessary for us to think about if we were to figure out backwards time travel and to go back in time to visit our ancestors or do some of these things? Like what are some of like the foundational philosophical things that we would need to consider, regulatory things that we would need to consider before doing something like this?
Yeah. To me, there was a great movie that illustrated this, science fiction movie. It was called, it didn't get the publicity that it should have because it was done very well, Time Cop with Claude Van Damme. It came out many, many years ago. And what it speculated about this, in fact, it even had the government involved in it. But the speculation is that it would have to be controlled by the government because you can't just arbitrarily go back into the past. Time travel to the past is not going to be something just like, everyone doesn't have their own nuclear reactor.
Right.
Okay.
Right.
The government, once it happens, it's going to be happening at the governmental level and it's going to be controlled. In the movie, what they have is Claude Van Damme plays a cop in the future. His job is to be a time enforcement officer. In other words, they have a mechanism to see that some change has been made in the past. They can see some early effect of that, and they send out these time enforcement officers to prevent that from happening. What makes the plot in this particular interesting, and I don't want to give the whole plot away in case people want to see it, is that this time enforcement officer, his wife had been killed in the past. And so he would have had the temptation, but he's never done it, of going to save his wife in the past. How can you imagine that being able to have technology at your disposal that you know that you could prevent a tragedy in your own past, but would you be able to have the willpower and the discipline not to do that? So it's not that easy. I mean, he can't just simply go in and have a private time machine to do it, even if he wanted to. But of course, the movie speculates and has its own people who realize that they can do this, that they want to change our reality.
Right.
So, but the thing is that there's going to have to be regulations, and there will be regulations if we do it. So there's two things going on. One, we should be trying to see whether we can develop the technology to do it. Mm-hmm. And at the same time, we should be thinking about the fact that once we do have that technology to do that, how are we going to regulate it to make sure that we do it in a way that's going to benefit ourselves and not something that's going to, destroy our world as we know it.
Yeah. Like, would you do it like time travel tourism, like where like only like the super billionaires get to travel back in the time to witness some of like the pyramids being built or Jesus Christ walking around?
Oh yeah.
Yeah, there was another thing that Mike Masters talks about in his book, the extraterrestrial model, is there was these kids, I think it was in like the 50s or whatever, where they saw these things, these human being looking things like in front of a spaceship, and they were answering all these questions for them. They were asking them about the universe, about the future of mankind, and all these questions about the past, and they were happily answering all their questions. And then one of the kids who was like a teenager at this time, he asked him about like religion and asked him about like Christ, and the being was like, we can't answer that question.
Yeah.
Like, would that, like, if by answering that question, how would that affect the ripple?
Well, in fact, that's it. The question would be, if we can change things, should we change things? How much information is too much information?
Yeah.
And that is, all of these things are things that come up. And to me, it's important to even speculate about these things, because eventually, if we find that we can do something, we will eventually do it.
Yeah.
I mean, because that's just our nature. Our nature is that once we found out we can control fire, that's led to where we are today. Yeah. And that happened millennia ago.
Yeah.
So it's going to be our nature. But at the same time, I love the fact that we have become wise enough to know when to put the brakes on ourselves. Just because of the fact that we can do something, should we do it? And if we do decide to do it, that we do it in a way that's going to be of the best for people generally to help us advance in a positive way.
How often do you talk to colleagues or people that are looking at the same kind of stuff you're doing, theoretical physicists that have studied the same thing, like and comparing ideas or getting pushback, or like what are some of even like criticisms that you've discussed or heard of about your work and your theory?
Yeah. Well, the criticism which I happen to agree with is there going to be enough power,
right?
And energy to do it, and how long is that going to take? I mean, I actually agree with with that. The other part is that my work is based on, its foundation is based on Einstein's work, and that's it. It's been published in peer-reviewed journals. So I know that it's the foundation of it is accepted, but the technological possibility associated with that theoretical possibility has its limitations, and I'm okay with that. I mean, that would be like, as I said, being prior to quantum mechanics, just looking at relativity and knowing the limitations that one has. In other words, I believe that technology can help us overcome limitations. One of the things I talk about in my book, in the prologue, is the fact that there was a very famous scientist in the end of the 18th century who talked about the fact that space travel, I'm talking about, air travel was not going to be possible. And he talked about all these reasons that it was possible. And then, of course, the Wright brothers showed that it was possible.
Right.
So the thing is that there's nothing in the physics that says we can't do it. But technology limits us to do it. But we have always been able to overcome the technological limitations. So to me, that's that I'm fine with the fact that right now it's technologically difficult, but that eventually we will be. I believe in human ingenuity. And that
it just feels like we've stagnated so much.
Well,
we're still flying around in airplanes that were built in the 50s. Like, it's so crazy.
But still, think about some of the things that were science fiction just in the 60s, the middle 60s. Your cell phone. Captain Kirk lived in the 22nd century, and his communicator, every kid on the block has a device, their iPhone or their Android, whatever phone. Their phones, their cell phones can do more than Captain Kirk's. The limitation that they had was just a limitation of imagination.
Yes.
So
even since the iPhone, though, like, think about it. The iPhone came out in like 2006, I think, and that was such a breakthrough. It just blew people's minds that we could have this thing that was touch screen and like no buttons, and it was just like the look of it was something from a sci-fi movie. And how long ago was that? That was like almost 20 years ago.
Yeah.
Like there hasn't been anything like that since. We've just been adding on to it, expanding it, making it smaller, making it a little bit better. But there hasn't been like a breakthrough like the iPhone in 20 years.
Yeah. But one of the things, though, Danny, that comes up is that, and one of the reasons why I like doing the interviews like this is the fact that people listen to these, people, and sometimes you never can tell. Someone's listening who has deep pockets, or someone who, a Bill Gates type or something, who says, maybe let's just simply look at this and see if there's any possibilities. You never can tell. I mean, that's the reason why I think it's for people to just keep their mind expanding. You just don't know when it's going to happen and where it's going to happen. And so me, that's why it's important for me, in any case, to keep, encouraging people to dream, to think about, these possibilities. And maybe sooner or later it will happen,
Yeah, and with like the amount of energy that you were explaining it required, you said like the energy of multiple galaxies.
Right.
It doesn't
potentially
seem, like our evolution, our technological evolution, where it's going right now is like started with fire. We have the way we fly airplanes and drive cars as we burn fuel and blow smoke out the back, propulsion, typical combustion engines that we have.
Right.
It doesn't seem like we're on the right trajectory to get there. It seems like that would take billions of years on the trajectory we're on right now.
The thing is that we have atomic power. Atomic power isn't any of these things. I mean, in Connecticut, we depend on atomic power for a lot of our electrical power. The thing is that we have parallel things going on. Okay, so it's not that we haven't made breakthroughs and that we don't have alternatives. It's just how much are we willing to invest in using these alternatives and making them of practical value. Okay, clearly having a small nuclear reactor for your vehicle isn't practical. However, having nuclear reactors for power is. To give you another example, thermonuclear energy. Thermonuclear energy, you're using you're using water as your fuel. That's, remember we were talking about the sun?
Yeah.
Okay. Hydrogen, what is water? Water is simply H2O, right? Okay. Hydrogen. If we cause fusion is the combination of hydrogen atoms together, okay, to produce helium. That's the opposite of ordinary fission reactors, okay?
Right.
And the type of that type of power would be unimaginable, and we're working on it. We're actually making strides. We should invest more in it, but when that happens, and it will happen, we're inching closer. Once we can do that, there's things like lasers. You see, people don't realize what we have done in the miraculous things that we've done. Einstein predicted the possibility of a laser back in 1917, rather. He predicted the basis for lasers, okay? It wasn't until the 60s that we did it practically, but once we did it, think of all the things that we do with lasers, and we don't even think about.
Right.
Okay? So all of these things are there. The theoretical basis for it is there. It's just that it's going to happen. Even with I was talking about the vast amounts of energy, that's a technological problem. We could find alternative ways of overcoming the energy barrier, then it will be, we didn't, I mean, looking at, once we're able to overcome it on a small level, it will be, gee, how come we weren't able to do this earlier? Lasers are a good example. It took from 1917 to the 60s before we had a real laser, but eventually we did. So to me, the theoretical basis is there for space and time travel.
Right.
Okay. The question is that when are we going to decide to invest in looking at the technology to achieve it?
Right.
And asking ourselves, how can we overcome these barriers to make it practical? And when we decide to do that, we will do it.
What do you make of the stories of those Navy pilots talking about those tic-tac things that were moving around? Are you familiar with the story?
No.
David Fravor, Commander David Fravor, he was a Navy pilot who was flying off the coast of San Diego in I want to say it was 2016. And this huge story broke on the New York Times, and they saw these objects on their radars. They weren't sure what it was, and it was right after they had upgraded the radars on their F-16s. This is one of them. This isn't the Tic Tac, but this is like one of the videos that was released by the Pentagon. You can turn the volume up on it and play it for them, and you can hear the pilots talking about it. So they're tracking it on their FLIR radar. And apparently this thing's moving at like ridiculous speeds, and they're having trouble like locking onto it. And you'll see at one point it just like breaks right out of their.
There's a whole fleet of them. Look on the ASA.
Here you go. Look at this.
Oh my gosh. They're all going against the wind. The wind's 120 knots from the west. Look at that thing, dude.
So that thing rotates.
Rotates like a gyroscope.
Yeah, well,
Look at that thing. It's rotating.
here's another one. This is hard to, it's. See, he's having trouble locking onto it.
Oh, got it! Woohoo!
Roger. There's troubleshooting.
Did you box moving target? No, I took an auto track. Oh, okay. Oh my gosh, dude. Wow, look at that, man. Look at it fly.
So Commander, those are a couple of those were on the East Coast too.
Right.
Commander Fravor is a lifelong Navy pilot, and he explained this whole story, laid it out beautifully, where he says that they were seeing these things on radar, went out to check them out, and it was like a tic-tac shaped white thing that was moving around in space. It was like moving around from one spot to the other. It would go from 10 feet above the ocean to 1,000 feet in like a split second. And he was also saying that like they were trying to track it. They were like trying to follow it and see what was going on. And he said like he was getting ready to fly to his cap point, which is like the entry point where the jets fly into their training space. And he said before he got to his cap point, after he was chasing the thing over there, it automatically showed up at his cap point before he even like knew that's where he was going. So he explains it's almost like the thing was time traveling. Like it was like traveling to where he was about to go.
Right.
And like following him, but in front of him. And it's just, like these things obviously defied any kind of gravity. There was no visible propulsion on these things whatsoever. And it completely defied the laws of physics to what we understand. And it's been like this topic of debate ever since this originally came out, and like I think it came out in the New York Times in 2020. But like if that's some sort of a military technology, that's crazy.
Yeah. The question is that what is it? And I
Exactly.
don't, and once again, for me, I have to see it under more controlled conditions. I mean, they see it. But
They saw it with their own eyes, and they have it on radar.
right. Nevertheless, there's other phenomena that we see. There's strange phenomena that are more like ball lightning and things like that. There are other type of phenomena, but once again, it's hard to say what it is that it is because we can't control it. We can't, actually get to it. Okay, so is it some sort of optical phenomena? I don't know. I mean, I really don't know, and I can't. I wouldn't be able to speculate because the thing is that I can't control it. That's part of the problem. Part of the problem is that I see that they see what they're seeing. It's real. But the question is it a real?
Yeah, for like the video of the one with the water in the background, it's possible that is an optical illusion where because the plane that's filming that is flying in one direction and the object they're filming is flying in the other direction.
Exactly.
So there's motion parallax with the water in the background.
Very good.
So when you're flying this way and something flying this way, it makes it look like it's going 20 times the speed.
Parallax, excellent. Yeah, that's a good example.
Yeah. But when you have somebody like Fravor, who's not like he's a guy who's like a lifelong military Navy veteran who's flying these planes his whole life, never interested in any of this like woo UFO phenomenon or whatever, that came out and basically said like, this is what I saw. And now there's other people that have come out like Ryan Graves, who was a pilot on the East Coast, who described seeing these things, and they called him to the Pentagon to have these like secret meetings with him to figure out what it was. And they developed this whole like safety protocol to avoid, because they were seeing them so much and nobody knew what they were. Yeah. And they were moving at incredible speeds with no visible propulsion whatsoever. And, the idea is that they were somehow figuring a way to manipulate gravity. And this is some of the stuff that Jack Sarfati talks about too, where there's different spectrums of light to where these things can like bend light and move through time. Like their propulsion is somehow gravitational time, and that's how they're moving around.
Yeah. Well, once again, for me, it's if we speculate that this is what's happening, why don't we just simply say, well, let's see if we can do that experiment? I mean, to me, it's like the equivalent of, whenever our very, very, very distant ancestors saw lightning, creating fire somewhere. Some one of them, some ancient male or female said, maybe we could do that.
Mm-hmm. Well, I think that stuff is ours. I think that the military has either figured this out and kept it secret forever, or it's somehow we discovered it and it's from somewhere else and we found a way to reverse engineer it, and we're testing it against our own military, testing it against our own Navy to see how effective it is, see how elusive it is, see how it can detect or be detected or not detected on radar. I think that's far more likely than the fact that it's like aliens or something like that.
Oh, I don't think it's aliens, but to me it's more likely that it is our own technology some way than it is aliens. But once again, it's hard to say. I mean, it's really hard to say. But to me, that would be more likely that it would be our own technology some way than it is from aliens. But for me, once again, the thing that is, well, if that's something that they're doing, then great. Why is it, however? I have this hard time with the military and keeping secrets.
Yeah.
I just think it would be too easy to leak. And the other thing is that for me, the exciting thing is why not just simply do it and share it, because then we can build on it.
Because we don't want Russia and China to know that we have it.
See, that's where the problem comes in for me.
Right.
It's the fact that it's more likely that they already know about it than our own citizens do.
Yes.
Because Russia knew more about the atomic, technology than we did, the average citizens. Why? Because they dedicate themselves to finding out our secrets, just as we dedicate ourselves to find out their secrets. So to me, it's more likely that China and Russia would know about it.
It would have to be some sort of plan between all these governments around the world to keep it a secret, right?
Right.
Like China, Russia, and the U.S. have to have a conversation like, look, we all know we have it. but we're not going to tell the population. We're not going to tell the people.
Well, that's actually what happened with atomic energy. I mean, because they knew about it before we knew about it, the average public.
Right.
You know, and the public didn't know about it until the end of the Second World War with Hiroshima and Nagasaki. You know, that's how we found about it. What's interesting when you bring that particular point up is the fact that they had the German scientists.
Yes,
they
the paperclip scientists.
Right. They had them all together at the end of the war before the bomb went off. They had captured them, and they were listening to them, their conversations, and they could not believe that we had been able to figure it out, the atomic bomb. They just didn't believe that it was possible. That's how arrogant they were about the possibility that it was only they would have been able to. And then they started accusing each other of maybe not working hard enough to develop the technology. And the thing is that, to me, once again, I think when I see something like that, Russia would be all over that. And they are good spies. They know what they're doing, And to me, if we are able to do that, then they have been able to figure out how to do that by reverse engineering too. If they see that that's a possibility, they would have someone in deep level spy who's been able to get the information about how we've done it, and they're able to do it now. So I just, I just feel that, as I said, I don't know, but I think that it would be interesting to see it. But you pointed out different ways in which this optical phenomena could occur. Parallax. You just mentioned that, so I think it's important to realize that.
Yeah. I think that's very possible that both things are happening. I think it's possible that there's some stuff out there that is very easily explainable that people think is crazy and crazy advanced technology. And I also think there's probably crazy advanced technology that's kept secret, black projects that are out there as well.
Yes.
And I think it's one of the things that the government, the intelligence community, whoever you want to call them, one thing that they're really good at is making reality very confusing with deception, strategic deception, and limited hangouts, and all different, and just putting all this information out there so nobody knows what's true.
Yeah.
And it's a good way to keep secrets, because you can let the truth can be out there, but then you can also throw some stuff out there that's complete bullshit. Right, that way you can't sort through it and figure out what's what.
Exactly.
That's what I don't know if you're familiar with Annie Jacobson. She's a journalist who wrote a book. Her first book was called Area 51, and she's wrote a bunch of amazing books after that. But Area 51, she talks about, how Area 51 was created. And when the first pilots started test flying, they were actually CIA pilots that started test flying the first jet planes over Nevada. Yeah. What they did was the CIA would send the pilots up into the air with gorilla masks in the cockpit. So that way, if a passenger plane came within visual distance of them, they were supposed to put on the gorilla masks. So if a pilot in a passenger plane says they saw some guy in a jet plane flying at the bar or whatever, he was wearing a gorilla mask. Now no one's going to believe the story.
That's funny.
And that's real. That was going on.
But I can believe that, because the thing is that they would say, oh, yeah, right. How many were you having?
Yes, exactly.
That's funny. But this notion of disinformation, you're right. If you put out too much, and some of it is true, but you're not able to discern or separate out what's truth and what isn't. You know? But once again, I think that's the reason why I'm a scientist, and I like that. It's because of the fact that electrons can't be deceptive.
Right. Right.
They're either they can do weird things, but I can predict within a reasonable amount what, I know that they're not trying to, I have a friend of mine that I say one of the things that's dealing with the subatomic world, I think of myself as being an empathetic person, but electrons don't cry, so I don't have to worry about, how they're feeling,
Right.
And I can make reasonable predictions that turn out to, always be, predictable. So once again, to me, when I see some unknown phenomena, I ask myself, what is it that I can think of within the laws of physics that might be able to reproduce that particular phenomena? Okay, and most of the time, you are able to. It's something that you can look at within the laws of physics. Okay, and I know limitations. I know that even though something can be traveling extremely rapidly, it's going to have to be within certain bounds of physics. And if it looks like it's out of the bounds of physics, then to me, I have to say there's something suspicious about this, So, but within the laws of physics, there's strange enough phenomena that I can feel comfortable with the fact that time travel, for example, which sounds weird to people, is possible. What I find is that most people don't realize that it is possible and that we actually have done it to the future. And that an exciting thing for me is to go into an audience and ask people, how many of you believe time travel is possible? Very few of the people raise their hands, except if it's a lot of young people in there. They
Right.
usually raising their hands.
Right.
But at the end of the talk, when I tell them about how it's based on Einstein's work,
Right.
and and I actually give them the examples, and then I ask them now how many people believe in the possibility of time travel, then they're willing to do that. And to me, that's my job. My job is to say, this is a weird, very strange universe, and it's stranger than we can even, imagine. But to me, what is exciting is, to quote Einstein, the incomprehensible thing about the universe is that it is comprehensible. No matter how strange it is, our human mind is able to eventually comprehend and control it. Imagine if you were to go into the 14th century or something like that, and you made a statement out that, we will be able to see everywhere all at once what's going on and everything. In other words, we talk about, what we do in every newscast, you would be immediately, burned at the stake.
Yeah. Right.
The thing is that what is science fiction for us? To me, it's just a scientific possibility of the future, just like the people in the past.
Right.
Okay. So the things that we've been talking about, to me, even though they sound strange, eventually we will be able to develop the technology, and there are things that we can't even begin to imagine. I mean, there were people in the past that the iPhone, before, they didn't even think of it as a possibility.
Right.
Let alone, something that we've developed and that we take for granted.
Another great example that we haven't even touched on yet is just look at how far AI has advanced in the last 2
good
years.
heavens, yes.
It's insane. Now people 5 years ago, to produce a video with graphics and voiceover and animation and music and all this stuff, you would have to manually go into a video editor, compile all these assets, make a video.
Right.
Now you can literally just type in a command into a prompt on an AI machine and it'll create a frigging video for you.
Oh, yeah. Yeah.
Ad agencies are using AI to do everything. They're using AI to figure out what's going to resonate the best with this specific audience and reverse engineer it from a bottom line perspective on what's going to be the most profitable way to make this commercial. How long should the commercial be? What should the people look like? What should the music be? All this stuff. It's being used for everything. And also going back to what we were talking about earlier with the time travel into the past and how to regulate it. I think AI would be a great way to we could use AI to tell us how to navigate the past and the right way to it. Like if we had to build a calculation, right, to go back in time.
What you're saying, a simulation.
To calculate how we can go back in time to not affect the timeline in a negative way or something like that. Like AI would be a way, if it keeps developing the way it's developing, to predict that or to create a framework to go by.
Oh yeah, no, artificial intelligence is going to be really fascinating as its way it's developing and developing onward to the future. You know, I mean, there's so many other things that we hadn't talked about, which go back to like the Matrix, and I'm just simply saying about what we keep forgetting about the fact that our brain is really our reality, you know, and everything that we're seeing and using and everything like that are just tools for our brain, but everything is here. And if we stimulate the brain in the right way, we don't know whether the thing that we're experiencing is really out there or just a stimulation of our brain, you know, and that's important because that means that sometime in the distant future, we may be able to do exactly that, to stimulate our brain so that we can experience a reality that is totally within our head. But as much as, you know, and I don't know whether you've experienced it or not, but this thing of lucid dreaming.
Oh, yeah.
You know, I mean, I just experienced that. This was now about over 20 years ago for the first time. I didn't even know what it was that I was experiencing. But I you know, was in a dream, and it was not like a scene that was strange, but I was on a campus, and at some point when I was in this dream, I realized that I was dreaming. Now, normally when you realize you're dreaming, you wake up; it just dissolves.
Right.
This didn't, and what I did was I was walking around the campus, and there were people sitting on the grass playing a guitar, and it was sunny. And I thought to myself, this is all in my head. But but as soon as I realized that I was dreaming, it was as though my brain was then putting in enough energy to make it even more solid. So it really felt like I was in a real world. But I also was aware that this was all in my head. So, but think about what that could mean for the future and for you know what we could do. You know, we're talking about virtual reality. We could actually no longer have it out there, but we could actually create worlds for ourselves inside that we really are living. It's incredible.
Yeah, there's the brain filter hypothesis that all of our senses, our vision, our smell, our touch are all filters to what reality really is. So that our brains can comprehend and so we can feed ourselves and get through the day and survive and evolve. And that you know, maybe what we see when we take mushrooms or psychedelics, maybe that's breaking down the filters of our brain and letting us see what's really out there. It's like ripping open the seams of the universe, or ripping open the fabric of the universe that is our senses, and letting us see more of what really could exist out here. Maybe all this other stuff is existing here, but we can't see it because our brains are filtering that out so that we can survive and we can breathe and we can eat.
Yeah, I mean, the thing is that I think that that's part of what, in fact, really is happening for us, that we do have, that our brain is filtering out.
Right.
Well, obviously, I mean, we know that we only see a portion of the electromagnetic spectrum, which is the light frequency. We can't see radio waves. We can't see X-rays and ultraviolet, but those are all part of the electromagnetic spectrum. Light is just a different frequency of all of that. I mean, imagine what it would be like if you could actually see radio waves, or you know, and we can down frequency that, which we do with ultraviolet. Infrared. You know, goggles and things like that. You know, which essentially is reality is just it's much more than we realize.
Also, speaking of dreams, have you ever heard of a guy named Eric Wargo? He wrote a book called Time Loops.
Oh, no.
About how dreams can predict the future and about how people can see the future in dreams. It's based off a guy named J.W. Dunn, who wrote a bunch of books about this. They call it precognition.
No, I'm not familiar. I mean, I'm familiar with the term precognition, but not with
Yeah,
this
there's like
particular
precognition, retrocausality, to where effects of something can come back in loops and affect the cause. Where like there's cause and effect, and like things that happen in the future can affect things that happened in the past. And is this idea called a time loop. And there's all these examples throughout history of documented dream accounts of dreams, people that were studying this stuff that would constantly document their dreams every time they dreamed, and where it would predict the future. And one great example that he gave was there was all these documented dreams that were documented before 9/11, where people had these dreams about 9/11 happening before it actually happened. And this goes back all the way to the Titanic. In fact, what was the, Steve, do you remember what he was talking about? There was a book that was written about the Titanic sinking before the Titanic actually sunk. You remember this?
I remember him talking about it. I don't remember the specific book.
See if you can find it, but it's incredible. He's gone really deep down this rabbit hole. And there's all this evidence that shows like he has this time loop idea, and there's all this crazy evidence that shows that dreams have actually predicted events that have happened in the future.
No, I'm not familiar with that. Of course, I mean this whole area that about what dreams, really are. As I said, with my experiences with lucid dreaming, has brought me to a whole different understanding of what the brain is capable of.
Right.
Yeah.
What I think the biggest evidence of time travel is this. This is a 3D print of an Egyptian dynastic granite vase. Okay, so these vases, there was hundreds of these vases that were found beneath a bunch of pyramids in Egypt. And they're made out of granite, diorite, some of the hardest stones in the world. Okay, this is the ship I was talking about, Futility. It was a novel written by Morgan Robertson, first published in 1898, and revised as The Wreck of the Titan. So it's called The Wreck of the Titan.
Oh, actually, I had heard of that.
In 1912, it features a fictional British ocean liner named the Titan that sinks in the North Atlantic Ocean after striking an iceberg.
Yeah, I had heard of that. I mean, that is weird.
And it's famous because it had similarity. It was obviously very similar to the real life. Go up a little bit. That shows a little bit more. The Sinking of the Titanic novel, and was reissued with some changes, particularly with the ship's displacement. So when did the Titanic actually sink?
1912. I think.
1912. Okay. So they changed it when the Titanic actually sunk. But this is just a great example. And this apparently was based off of a dream this guy had, and wrote this story about the Titan.
There it is, precognition.
Yeah. So after the Titanic sinking, some people credited Robertson with precognition and clairvoyance, which he denied. Scholars attribute the similarities between Robertson's extensive knowledge of shipbuilding with maritime trends. Sorry, it could have been a coincidence, but he brings evidence to brings forward lots of evidence of these precognitive dreams happening, which is pretty wild.
Yeah.
So anyways, about this vase. These were, according the academic consensus to archaeologists and Egyptologists, is that these were created 4,000 years ago, 4,500 years ago. So, and they're made out of the hardest stone, one of the hardest stones in the world, which is like red granite, a lot of them. And they brought these into a aerospace company in the U.S. and they measured them with laser scanners. And they found out that they're perfectly symmetrical with the deviation at every point. Like they measured here, they measured the inside here, they measured the outside, everywhere around here, from here to here, is perfectly symmetrical within the deviation at the worst part, where it's like the most asymmetrical, is within like a fraction of a human hair.
That's incredible. I mean,
and the idea and consensus is that the Egyptians were using copper chisels and pounding stones back then to shape rocks and stuff like that. And today, there's no way we could recreate this unless it was on like a CNC laser machine.
Right. I was thinking of that. Yeah.
So there's absolutely no explanation to how people 4,500 years ago were able to create that. Like, we have no evidence of technology they were able to use to do this. They didn't have lathes, right? and it was made out of the hardest stones in the world.
Huh.
And then it's all like the handles are built out of it. Like they're not added on, right? The handles are it's
built,
all
yeah.
one piece of granite. And it's so
That's remarkable.
unbelievably perfect and symmetrical.
That's weird.
I think that's time travel. I think that's future humans coming back and dropping some Easter eggs for us.
I don't know.
And there's other things that are out there too. There's like giant, like megalithic, like 1,000-ton obelisks that that are created, and it just does not fit up with the conventional understanding of how they were able to, like, there's scoop marks out of granite. Like, we don't know how they were able to do that. And the conventional, if you ask an Egyptologist or like an older some of the younger Egyptologists are kind of like more open to like looking for ways they would have really done this. But like some of the older Egyptologists, you know, they're just stuck in the dogma of pounding stones and copper chisels to do this stuff, but it just doesn't fit. It doesn't make sense.
I mean, the thing is that what it makes you wish is that things like the library at Alexandria, you know, could have been preserved. I mean, how much knowledge did we lose by that, you know?
Right.
I mean, it's
wild stuff.
Yeah, really.
Well, Ron, thank you so much for coming and doing this.
Oh, it's really my pleasure.
Yeah, I really enjoyed this conversation, man. Tell people, well, yeah, we're going to do a Patreon Q&A. As soon as we wrap this up, we got some people on Patreon ask you some questions. We're going to go do that. But in the meantime, where can people find more of your work online? Where can people get in touch with you online?
Well, the main place to both, you mentioned it, is my book, Time Traveler. I should mention that the book is co-authored with the New York Times bestseller, Bruce Henderson, who's my co-author. And the book talks about not just simply my life, but it talks about the real scientific possibility of time travel and many things that we didn't get a chance to talk about, other possibilities, cosmic strings and things like that. But this would be the best source. And you also mentioned the fact that there's a documentary. There's actually two documentaries. One is How to Build a Time Machine, which is a beautiful documentary.
Yes.
That's won a number of awards. And there's another one that's called The World's First Time Machine. It's a BBC documentary that came out many years ago. That's also a nice source. Both of these are available. Well, let's see. I think How to Build a Time Machine, I'm not sure whether it's on YouTube or not. But it is available, and the How to Build the World's First Time Machine is available on YouTube as well. So, and I'm on Facebook too, you know, so people can contact me, you know, there.
Perfect.
Okay.
I'll link it below.
Yeah.
All right, Professor, thank you so much for your time.
Sure, thank you.
All right, we're going to go do Patreon. Goodbye, world.